Industrial processing plants are built on a continuous flow of material, but when that material takes the form of a thick, mixed-phase slurry, a heavy blend of liquids and solids, processing it quickly becomes a massive engineering bottleneck. You have to separate the phases to keep the plant moving. Pumping the slurry into a traditional settling tank and waiting for standard gravity to pull the heavy solids to the bottom is slow. Worse, it forces a hard stop. You eventually have to halt the entire process, drain the tank, and dig out the accumulated sludge before you can start again. This is an industrial decanter centrifuge. It is a mechanical solution designed specifically to bypass the limits of standard gravity and achieve continuous, high-volume phase separation without ever breaking the feed cycle. The technical nameplate reveals the physical force generated. Operating at 3,800 RPM, the assembly creates a centrifugal force 3,558 times Earth's gravity. This acceleration allows processing of solid cakes with densities up to 1.2 kilograms per cubic decimeter without overload. By magnifying gravity by a factor of over 3,500 inside a specifically engineered geometric enclosure, the machine forces dense solids to drop out of suspension almost instantly. If we strip away the blue outer structural frame, we expose the rotating assembly, the core where the actual separation physics take place. This main outer bowl consists of two primary geometric zones. First, a long cylindrical section where the liquid settles and clarifies. Second, a tapered conical section at the far end, known to engineers as the beach. When a mixed slurry is pumped into this high-speed environment, it is immediately subjected to the massive G-force. The physics act strictly based on phase density. Inside the spinning cylinder, heavy solid particles are rapidly driven outward, pinning tightly against the inner bowl wall. The less dense clarified liquid forms a distinct floating inner cylinder, resting directly on top of the compactive solids. But a simple spinning bowl has a design flaw. It separates the phases perfectly, but the heavy solids quickly build up against the outer wall. In a matter of minutes, the bowl fills up, chokes the fluid flow, and requires a complete shutdown to scrape clean. High kinetic energy solves the separation problem, but creates a severe extraction problem. The very force used to isolate the solids leaves them trapped against the outer wall. The engineering solution to this buildup is nested directly inside the rotating bowl, an internal screw conveyor. This component is designed to dig out the compacted solids, while the machine remains at full operational speed. It does this through a mechanical principle known as differential speed. The conveyor rotates in the exact same direction as the outer bowl, but at a slightly different rate. The outer bowl spins at a constant speed x. The internal conveyor is geared to spin at speed x minus delta x. This speed difference is maintained by a backdrive motor and planetary gearbox, locking the rotation ratio. Because of this relative motion, the conveyor's helical flights act like an Archimedes screw, continuously scraping the heavy solids off the inner bowl wall. The screw drags this compacted material horizontally out of the long cylindrical settling zone, and then forces it up the dry incline of the conical beach. Reaching the very edge of the cone, the solids are finally pushed out of the machine through distinct discharge ports located in the small end hub. This differential speed creates a mechanical bridge between batch separation and continuous extraction, allowing the machine to clear its own path while in motion. Inside the spinning assembly, the material splits into two opposing flows. The heavy solids are mechanically scrolled toward the conical end, while the clarified liquid naturally overflows toward the large end hub. The total volume inside the spinning bowl occupied by both the liquid and the solids is called the pond. The pond's physics are dictated by three geometric lines: the central axis of rotation, the liquid surface radius, and the solid's discharge radius. Operators adjust the liquid radius using dam plates or power tubes, raising or lowering the level. When the liquid level is configured to be exactly equal to the solid's discharge radius, the setup is defined as a neutral pond. If the liquid level is raised higher than the solid's discharge port, it creates a positive pond. This maximizes the volume of liquid in the bowl, giving the fluid more time to settle and improving liquid clarity. Conversely, dropping the liquid level lower than the discharge port creates a negative pond. This exposes a section of the conical beach, creating a dry zone. A negative pond maximizes the physical compaction and dryness of the solid cake before it exits. However, it requires running the machine at a lower differential speed. The solid matter has to form a dense physical barrier on the beach to prevent the liquid from escaping out the wrong end. Manipulating this geometric relationship between the pond depth and the discharge radius is the primary tuning lever engineers use to optimize a plant's separation efficiency. Backing out from the internal fluid dynamics, we have to look at the external hardware, like the main drive motor and the rigid steel frame, required to physically contain this operation. A solid steel assembly of this mass, spinning at 3,800 revolutions per minute, possesses enormous kinetic energy. The forces at play are highly destructive if not managed. The main bearings bear the extreme brunt of this rotational force. This is precisely why these yellow transport safety wedges are bolted into the bearing housings to lock the assembly whenever it is powered down for transit. During operation, the greatest physical danger is mechanical unbalance. Even a minor, asymmetrical buildup of solids inside the bowl multiplies under 3,500 Gs, threatening to tear the machine off its mounts. The operator's manual explicitly prohibits starting the centrifuge if there is frozen or hardened material inside the bowl, because that solid, uneven mass guarantees a severe unbalance on startup. To prevent this, strict shutdown protocols must be followed. The slurry feed is stopped, and the bowl is scrolled out and flushed empty with water before the main drive is allowed to come to a complete standstill. The mechanical architecture is highly effective, but it is only capable of continuous separation if operators actively manage its internal equilibrium and respect its kinetic energy. When we bring all these separate mechanical elements together, we see a coordinated system operating at peak efficiency. The feed enters the center, separates, and discharges simultaneously from both ends at exactly the same rate. The entire process rests on three structural pillars: centrifugal force to drive separation, differential mechanical scrolling to extract the solids, and precise internal fluid geometry to optimize the phase layers. The result is the ability to take a turbulent mixed feed stream and reliably divide it into two highly valuable clean output streams. Sustaining this balance requires strict operational discipline. The machine relies on maintaining the exact differential speed and the correct physical pond depth to prevent choking or unbalance. The decanter centrifuge provides a mechanical platform for balancing fluid dynamics and rotational kinetic energy. By precisely tuning these internal variables, operators can extract specific phase purities at scale, day after day, without stopping.